Welcome to today's webinar. The topic today is structures with reinforced aluminium sections in our section 1 and RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, technical content of the website, German and English webinars, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Bloor will be the presenter. She's responsible for product engineering and customer support. And she's the main responsible person for the add-on aluminium design and also for our section. Okay, then I say something how you can ask questions. At first I switch off my webcam that you can see the full screen. You can press that button with the question mark, and then you can enter your question here, press send, and I will receive your question and I will answer you. Okay, that's all from my side. I hand over to Sonja. Sonja, it's your turn.
Thank you, Andreas, for the introductory words. I would also like to welcome you to today's webinar. The topic of this webinar is the modeling of structures with reinforced aluminum cross-sections. The reinforcement can be made of steel or aluminum. There are several options for creating these reinforcements. The aluminum cross-section, including reinforcement, can be created as one cross-section in our section. Another option is to model two separate members in RFEM or RSTAB with the respective aluminum or steel cross-section. I will first show the modeling of the aluminum cross-section, including reinforcement in our section, and afterwards I create the structure in RFEM. In the process, I will also explain how to change our section cross-sections from RFEM. I then model the structure with two separate members using line releases in RFEM. I will then show an alternative modeling of the two separate members using nodal releases in RFEM. This option is also available in RSTAB, while line releases are not available in RSTAB. Finally, I will talk about new useful features. This brings me to the first point, the modeling of the aluminum cross-section, including reinforcements in our section. The cross-section geometry is available in DXF format so that I can use the import function. The creation of cross-sections based on DXF files was the subject of a previous or section webinar. You can find this webinar on our website or on YouTube. There's also a knowledge base article on this topic on our website. I start the import process via File, Import, DXF. Then I choose the corresponding DXF file and click on Open. In the import dialog, I select the option Create DXF template for further editing. And then I click on OK. Now the lines of the DXF files will be created in our section. I first create the part using the function select boundary. Here I have to define the material. I want to use this material that's already chosen here in this box. Then I click on OK, and then I click on the corresponding line. The part is now created. Now I have to create the opening. For this, I select also the function that's available for openings to select boundary, and then I click on the corresponding line. I then deactivate the display of the parts and openings to get a better overview. I then create the elements necessary for the classification and calculation of the effective cross-section. To do this, I only model a quarter of the cross-section, and I then create the other parts by mirroring. To do this, I use the set center lines function. I find this function here in this part. All I have to do is click on the two parallel lines. The center line is then generated automatically. First, I create the center lines for the flange, then for the arc, and then for the web. The center lines then need to be extended. For this, I use the function extend graphically. Clicking on the left side of the line to be extended extends the line to the left. Otherwise, to the right until it intersects with the next line. I will extend here this line to the left, and I want also extend the center line of the web on both sides. Since I only want to model a quarter of the cross-section, I trim the center lines accordingly. To do this, I use a function that I find here that's called toLocation. This function makes it possible to extend or shorten a line to a specific location. I trim the center lines of the flange and the web to the center of the cross-section. To do this, I select these two lines, and then I click on OK. I then have to specify the side of the line to be modified. The direction of the lines is shown on the working area. I have to shorten the end of the line, so I choose this in this list box. Then I have to define the location in this part here. I choose the 0 point here, and then I click on OK. Then the center line of the arc has to be connected to that of the web. And I make this connection with a straight line. For this, I create here a new line, and I connect it here. I don't need this line here, so I delete it. Now, this line is not divided at this point, but this is necessary that it's divided because elements are only connected if they share the same node. For this reason, I divide this line in this location. To do this, I use the function connect lines and elements, and I draw a window about this part, and now the line is divided in this point. I can now create the elements using the create elements online function. I find this function here, create elements online. All I have to do is to select the corresponding lines. I select all the center lines. I click on OK, and then I have to define the thickness of the elements, and here I define 5 millimeters. Now the elements are created. I now select all elements here in Navigator Data, because I want to mirror them. For this, I choose here this function mirror. I want to create a copy, so I activate this option. Then I have to define the mirroring axis. It's the axis Z, and the point, it's the 0 point. And I click on OK. Now the right part is created, and I need here the part on the bottom. So I select all of my elements and I open the dialog mirror copy again, and I change here the mirroring axis to axis Y. And then I click on OK. I then create the reinforcement. This consists of a welded rectangular cross-section made of S235 steel. I import this cross-section from the RSECTION cross-section library. To do this, I go to Navigator Data and choose here New Section. Then I open the section library and choose the rectangular hollow section. This should be a welded rectangular hollow section, so I choose here the manufacturing type welded. I have also to create a new material. I want to use steel S235 for this cross section, so I create a new material, open the material library and choose here S235 from this standard. Click on OK. OK, and then I have to define the geometry of this cross-section. Height is here 230 millimeter, and the width is 100 millimeter, and the thickness is 5 millimeter. In the top section location rotation mirroring, I select here the 0 point as the insertion point, and I click on OK. Only cross sections that are rigidly connected to each other can be imported into RFEM 6 or RSTAB 9. This connection is applied over the entire length of the member. If the cross sections are not connected to each other, the modeling presented here is not suitable. Two members would then have to be created in RFEM or RSTAB. As I mentioned at the beginning, I will also show this today. In order to connect the two cross sections, I have to explode the cross section into its individual objects. To do this, I choose here this cross section and choose here this function explode. I create the connection between the two cross sections using an element with a 0 thickness. To do this, I open here this function new element, define a thickness of 0 millimeter, and I have to define also an effective thickness for shear transfer, and this will be 5 millimeters. Then I create the two elements In the base data, I open it here, I set the thin-walled analysis method. This is necessary because the connection of the two cross-sections was made using elements with zero thickness. These cannot be taken into account with a finite element analysis. The connection of the two cross-sections would have had to be made using parts. It's advisable to start the calculation once in order to find possible modeling errors. Here, no errors will be found, so I save now this cross-section. I name it here reinforced Alu section. Then I can close this cross-section. I now can model the structure in RFEM. So I open RFEM. Here I have already created a new file, and I have to import first the aluminum cross-section with the reinforcement that I've just created. To do this, I go to Navigator Data, choose here New Section, open the section library from our section, and I choose here the reinforced aluminum section. I still need this cross-section without reinforcements, and for this I want to show you a new function in RFEM or RSTAB. In RFEM or RSTAB, it's now possible to open this cross-section in our section and to modify this cross-section in our section and to import it again in RFEM or in RSTAB. To do this, I copy this cross-section and then I open this cross-section in our section. In our section, I then delete the steel cross-section and the connection between the steel cross-section and the aluminum cross-section. Then I start the calculation again to see if there are any errors. There are no errors, so I can save this cross-section. I want to save this cross-section also on my disk, so I choose here File, Save As, and I change the name to Alu section, and then I save this section on my disk. Then I save this section. I go to Save and Return to RFEM, and by clicking Save and Back, I also apply this change in RFEM. You can see now this cross-section is without this reinforcement, and this cross-section includes this reinforcement. If I had just clicked Save and Back, only the cross-section would have been changed in RFEM, but the original status of the cross-section would have been left on the hard drive. Then I click here on OK. I then model the column with the unreinforced aluminum cross-section. I choose here New Member, choose the aluminum cross-section, and then I define the column with the height of 6 meter, and I model the beam with a length of 8 meter. The roof pitch is 18 degrees, so I use the function chamfer. I find this function in menu edit, manipulation, chamfer. Here I have to define the angle, the rotation angle of 18 degrees, and I have to define the rotation axis. This is the axis Y, and the rotation direction, and this is the direction Z. Then I choose the frame corner as the rotation point. Now this beam is rotated by 18 degrees. The frame corner is reinforced with a steel over length of 0.5 meter. I therefore divide the column with this functions by distance, and here I define a length of 0.5 meter. Apply this, and I have to do this also for the beam. But here on member start. Now the column and the beam are divided into 2 parts. I then define hinged supports at the beginning of the column and the ridge. To do this, I assign a nodal support here. On the column and on the ridge. Since I want to show different modeling options today, I copy the frame twice. I use here the move copy function and activate the create copy. Number of copies is 2, and the displacement vector is 10 meter. First, I will show the modeling of the reinforced frame corner with the aluminum cross-section and reinforcement that I just created in our section. To do this, I only have to change the cross-section in the frame corner. I choose here the 2 members, choose Edit, and then I choose here the reinforced aluminum section. Then I have to define the load. I do not want to consider the self-weight, so I deactivate the self-weight in this load case. And then I create the member load. here a load direction global in Z on projected length with a load magnitude of 2.6 kilonewton per meter. And I define it on these two members. The disadvantage of this modeling is that it's not possible to design cross-sections with different materials in add-on aluminum design or steel design. However, the stresses can be determined in the add-on stress-strain analysis. In addition, I cannot define the coupling conditions between the aluminum and steel cross-sections. So with this type of modeling, I cannot define that the aluminum cross-section is only slide over the steel reinforcement, and thus the steel cross-section only supports bending. The axial force here acts at the entire cross-section. If I here start the calculation, I will see this in the internal forces. However, both mentioned disadvantages can be avoided by modeling two members. First, I would like to show you an option that is only available on RFEM. This is the modeling using line releases. A line release allows the model to be decoupled along a line. I would like to show you the principle in my presentation. For this, I go to my presentation. Shown as member 1 on line 1, which is defined by nodes 1 and 2. First, I have to select the line on which the line release is to be defined. Furthermore, the properties of the line release must be defined. This definition is made in the line release type. The property of the line release are described by a hinge. The line releases create nodes 3 and 4 as well as line 2, which is defined via these nodes. The generated released objects are output in the release generation part here. The lines are coupled along their length using the hinge condition defined in the line release type. This is indicated by the coupling bars shown on the graphic. The position of the line hinge can be defined in the section release generation 2. It can be defined on the original line or on the released line. This is defined here on the original line. In this example, this is the line 1. The released line is automatically created with the corresponding nodes as a copy. However, if you want to use one or more existing nodes for the generated line, you can specify the corresponding node numbers in the section definition objects. This affects the results because the displacements at these nodes are not released. So for example, if you define nodes 1 and 2, as here on this example, as definition nodes, the released line is defined using the original nodes 1 and 2. I can now define the member on line 2 and then specify it as a released object. This is this member number 2. I would now like to show you the modeling in RFEM. For this, I go back to RFEM. First, I create a new line release. I go to Navigator Data and I find the line releases under Special Objects, Line Releases. Here I create a new line release. I then select the corresponding lines. These are the lines 7 and 6. After that, I create a new line release type. The displacement in the X direction should be released here. Click here on OK. And this line release creates the line 13 and 14 on the release nodes 16 till 18. On lines 13 and 14, I open it here in the Navigator Data. I now define the reinforcement cross sections. To do this, I choose the two lines, click on Edit, and I apply a member on these lines. And I choose here, or I have to create here a new cross section, and this should be the welded rectangular hollow section. To do this, I open the section library, choose here rectangular hollow section. This section should be welded, so I choose the manufacturing type welded and the material S235. Now I have to define the geometry. The height is 230 millimeter and the width is 100 millimeter and the thickness is 5 millimeter. Then I click here on OK. And now the member is applied on this line. To ensure that the aluminum cross sections are all connected to one another, they must be defined using the original nodes. The steel cross sections must be defined using the released nodes. I control this using visibilities. For this, I go to the Navigator Views and first I will show here the steel cross sections. These are defined using the release nodes, and the release nodes have here a blue color. If I move the mouse over the node, a reference to the associated line release is also displayed. You can see it here. Then I only show the aluminum section, and the aluminum section are only defined using the original nodes, and the original nodes have a red color. Since the aluminum cross-sections are only slide over the steel reinforcements, I still have to define movement hinges on the aluminum cross-sections in the frame corner here. For comparison purposes with the other structure, I will not show this today. I then define the member load of 2.6 kilonewton per meter on the aluminum beams. To do this, I choose here the new member load and define it on these beams. Then I start the calculation. I first look at the axial forces, and the axial force is applied only on the aluminum cross-section. If I show here the steel cross-section, I see that no axial force is applied here. This is because we have defined the line release with the release in X direction. Then I show the bending moments here on all cross sections, and then I see here the bending moments are applied to both members via its stiffnesses. The bending moments are applied on the steel cross section and on the aluminum cross section. As already mentioned, line releases are only available in RFEM. However, modeling with two separate members is also possible in RSTAB. Nodal releases are available for this in RSTAB. You can also use nodal releases in RFEM. I would like to show you the principle in my presentation. Shown is member 1, which is defined via nodes 1 and 2. First, I have to select the nodes at which the release is to be defined. Furthermore, the properties of the nodal release must be defined. This definition is made in the nodal release type. The properties of the releases are described by a hinge. The position of the hinge can be defined in the section release generation on the original node or on the released node. I also have to specify the released objects. This is the member number 1 in this case. The nodal release creates the release nodes 3 and 4. The generated released objects are output in the section release generated here. The nodes are coupled via the hinge conditions defined in the nodal release types. You can see it here. Member 1 is now defined between the released nodes 3 and 4. Member 2 can now be defined between nodes 1 and 2. It should be noted that in contrast to line releases, the two members are only connected to each other at nodes 1 and 3, here at this part, and at nodes 3 and 4, but not over the length of the member. If the coupling conditions are to be applied along the length of the member, in the solution with nodal releases, the two members would have to be divided at the small intervals and nodal releases defined at the intermediate nodes. I would now like to show you the modeling in RFEM. For this, I open RFEM again. First, I have to create the new nodal release. I go here to the navigator data and I find the nodal releases here under special objects, and I create here a new nodal release. Then I select the corresponding nodes. These are the nodes 14, 12, and 15. The nodal release type should be defined separately for each node because the reference axes are different. So I activate here this checkbox, define nodal release type for each node separately. Then I go to the tab nodal release type, and here I have to create a new nodal release type for this node 12. And here, once again, the displacement in X direction should be released. Then I have to define the local axis system, and I choose here the local axis system from this member. This release should be also used for node number 15. And for node number 14, I have to create a new nodal release type. Release is also in X direction, but the member is here, the member number 9. Then I have to define the released objects, and these are the objects 11 and 10. The generated release nodes are 19 till 21. Then I click on OK. The released aluminum members are now defined via the released nodes and no longer via the original nodes. In order for the aluminum cross-section to be connected to one another, they must all be defined via the original nodes. Therefore, I now change the cross-section of the released members I choose here Edit to the steel cross-section. I then define the aluminum cross-sections between the original nodes. To do this, I open here the new member, choose here the aluminum cross-section, and then I choose here the original nodes for the definition. I check this again using the visibility. For this, I open the navigator views and activate the visibility. for the steel cross-sections. The steel cross-sections are defined via the release nodes. Release nodes are colored in blue. I can see it here, and if I move with the mouse over the node, I see this is a node created via a nodal release. Then I show the aluminum cross-sections only, and the aluminum cross-sections are defined via the original nodes. The original nodes have a red color. I can see it here if I move the mouse over the node. Since the aluminum cross-section are only slide over the steel reinforcement, I still have to define movement hinges on the aluminum cross-sections in the frame corner. As I mentioned before, for comparison purposes with the other structure, I will not show this today. I then define the member load on the beam, on the aluminum beam, with the same load magnitude. And then I start the calculation. I first look at the axial force. Due to the hinge defined in the line release in X direction, the axial force is only transferred via the aluminum cross-section. You can see it here. If I show the steel cross-section, no axial force is applied here. The steel cross-section also contributes to bending. I will show you this also. If I show here the bending moments My, I show it on the whole cross-section, and you see that both members have a bending moment. This brings me to the last point of today's webinar, the new features. You can now also read results such as the member sec from the dimension. To do this, a linear dimension must be defined on the member. I now define a linear dimension on the beam. And to see here also the results, I have to go to the navigator results, and I have to activate under dimension the results on member. If I want to see the deformation, I activate here the global deformation, and I see now the result here on the dimension related to the deformed system. A member sec corresponds to the largest dimension of an imaginary line between the deflected beginning and end of the member section. The supports are very stiff, so the member sec differs only slightly. Here the member sec is 24.1 millimeter in comparison to the global deformation of 24.2 millimeter. if I define a dimension between the end of the reinforcement and the end of the beam, the difference will be clearly visible. I do it here. I choose here the two nodes. And you can see here the sec deformation is now 22.5 millimeter in comparison to 24.2 millimeter for this section here. Another new function allows you to examine the stresses within members using clipping planes. Clipping planes are cutting planes that you can freely place through the model. The area in front or behind this plane is shown transparently in the view. The predefined clipping planes can be used for this, and you find these predefined clipping planes in the navigator data. Here under guide objects. Clipping planes, and we have here three predefined clipping planes. However, it's also possible to define user-defined clipping planes. I want to activate the clipping plane, so I choose here clipping plane on. And I want to examine the normal stresses here in the member. Therefore, I choose here the display of the stresses. I can then move the clipping layer to the desired location with the mouse via these. I can see now the stresses here in the cross section. And here in the cross section of the unreinforced part. This brings me to the end of the webinar. I will now hand the floor back to Andreas.
Thank you, Sonja, for your presentation. An additional hint from my side, you can book your free online appointment, such as a product demonstration of our add-ons or main programs. You can click on that link in the PowerPoint, or you can scan the QR code, and then you will, or you can contact the sales team. You can download the PowerPoint slide from the webinar page. In the next days, you will get an email when the recording is online with a link to the webinar page, and you will also get your attendee certificate. And on the webinar page is also the PowerPoint slide, model, and the recording. Okay. That should be also all from my side. Thank you for your attention. Thanks to Sonja for the nice presentation. I wish all a nice rest of the day and say bye-bye.